is type of acid and bases. So there are two types of acid. The first one is strong acid and weak acid. So first we are going to look at what is meant by strong acid. Okay, strong acid is acid that dissociates completely in water to produce high concentrations of H plus or H3O plus. It undergoes 100% ionizations, or its degree of dissociations is equal to 1. For example, HCl. HCl or hydrochloric acids is one of strong acids. This acid is fully ionized in water and form very high concentrations of H3O plus and Cl minus. This reaction is irreversible, which means that the reactions cannot be reversed. So there is only one arrow in the chemical equation, which is the forward reactions. Another strong acid is HNO3, which is nitric acid. So nitric acids also undergo complete dissociations in water to form very high concentrations of H3O plus and NO3 minus. Okay, next is strong base. Strong base is a base that dissociates completely in water to produce high concentrations of OH minus. So it's undergo 100% ionizations, or the degree of dissociations is equal to 1. For example, sodium hydroxide. Sodium hydroxide is one of the strong bases that undergo complete dissociations to form Na plus and OH minus. Another example of strong acids is HBr and HI, other than HCl. HNO3, H2SO4, HClO4. And for the strong base is group 1 metal hydroxides, for example, lithium hydroxides, sodium hydroxides, KOH, RbOH, CSOH, and also group 2 metal hydroxides, CaOH2, SrOH2, BaOH2. Okay, next is weak acid. Weak acid is acid that dissociates partially in water to produce a low concentrations of H plus or H3O plus. So it's the percentage of dissociations is less than 100, or its degree of its dissociations is less than 1. For example, CH3COOH. CH3COOH is one of the weak acid. So this acid is not fully ionized, as it's undergo only partial dissociations to form CH3COO- and H3O+. This reaction is reversible reactions. So there is two arrows, forward and reverse, in the chemical equation, and the reaction is in equilibrium. Example of weak acid is HF, and also acid in which hydrogens not bonded to oxygens or halogens, for example HCN and H2S, oxo acids HClO, HNO2 and H3PO4, and also organic acids that has general formula RCOH, for example CH3COOH and C6H5COOH. So this is the graphical presentations of dissociations of strong and weak acid. So from this graph, let's look at the strong acid. So before the dissociations, this is the number of mole of strong acids, which is very high. But after the dissociations, there are a large amount of H3O plus and A minus produced, and these are the product. And there is no reactant remained after the dissociations. So this shows that all acids ionize into ion. But for the weak acids, here is the number of mole of weak acid before the dissociations. And after the dissociations, it shows that there are large amount of weak acid remained, and there are only small amount of H3O plus and A minus produced. This shows that weak acid undergo partial dissociations, or in other words, not all weak acids ionize into ion. Weak base is a base that dissociates partially in water to produce a low concentrations of OH ion. So its percentage dissociations is less than 100, or its degree of dissociations is less than 1. For example, NH3, which is ammonia, that undergo partial dissociations in water to produce NH4 plus OH minus. Please keep in your mind that these reactions is reversible reactions. So there are forward and reverse reaction. Example of weak base is a molecule with nitrogen atom that has a lone pair electrons. For example, ammonia, and groups of amines such as CH3, CH2, NH2, and hydrazine, N2H4. pH, POH, and pKw. The hydrogen ion H plus concentrations in a solution is measured using pH scale method. So the formula is pH equal to negative log concentrations of hydrogen ion. So the pH is defined as the negative logarithm of the hydrogen ion H plus or H3O plus concentrations. If the concentrations of hydrogen ion increase, the pH will be decreased. For base, concentrations of OH minus is measured using POH. So the formula here is POH equal to negative log concentrations of hydroxide. The POH is defined as the negative logarithm of the hydroxide ion. If the concentrations of hydroxide ion increase, the POH will be decreased and the pH will be increased. Ionic product of water, Kw. Water molecule can be undergo auto ionizations. They will transfer a proton from one water molecule to another, producing a hydroxonium and hydroxide ion. So this is the equation for the water ionizations. So when water undergo ionizations, it forms H3O plus and OH minus. So this equation is reversible reactions, and since this reaction is at equilibrium, so it has its equilibrium constant expression. So the equilibrium constant expression Kw is equal to concentrations of H plus times with the concentrations of OH minus. In this case, water is a liquid, so we don't include that in these expressions. Kw is the ionic product of water at 25 degrees Celsius. In pure water at 25 degrees Celsius, the concentrations of hydrogen ion and hydroxide ion are equal. That is 1 times 10 to the negative 7 molar. So by using the equilibrium constant expressions Kw of water, that is Kw equal to concentration H plus times concentrations OH minus, when we substitute the concentrations value, we can get Kw equal to 1 times 10 to the negative 14 molar square. Next is the relationship between pH, pOH to ionic product of water, Kw. By using the Kw expressions, we put the negative log at both sides of the equations. So we can get negative log Kw equal to negative log H plus negative log concentrations OH minus. So negative log Kw is equal to pKw, negative log H plus is equal to pH, and negative log OH minus is equal to pOH. So at 25 degrees Celsius, since Kw is equal to 1 times 10 to the negative 14 molar square, we substitute these concentrations with the pKw, so we can get negative log times 1 times 10 to the negative 14 equal to pH plus pOH. So negative log 1 times 10 to the negative 14 is equal to 14. So finally, we can get 14 equal to pH plus pOH. So from this formula, we can use to calculate pH or pOH. Please note that the value of Kw increase with temperature because the dissociation of water is an endothermic process. For aqueous solutions at 25 degrees Celsius, for the acidic solutions, the concentrations of H3O plus is greater than concentrations of hydroxide ion. So, the concentrations of H3O plus must be greater than 1 times 10 to the negative 7 molar. And the concentrations of hydroxide ion must be less than 1 times 10 to the negative 7 molar. For the neutral solutions, the concentrations of both ions are equal. That is 1 times 10 to the negative 7 molar. For the basic solutions, the concentrations of hydroxide ion is greater than concentrations of H3O plus. That means the concentrations of hydroxide ion must be greater than 1 times 10 to the negative 7 molar. And the concentration of H3O plus must be less than 1 times 210 negative 7 molar. The pH scale is divided into 3 parts: acidic, neutral, and basic. For the acidic, the concentrations of hydrogen ion is greater than concentrations of hydroxide ion. For the neutral, concentrations of both ions are equal. And for the basic, the concentrations of hydroxide ion is greater than hydrogen ion. So this is the combinations of the pH and pOH scale. If the pH is 0, the pOH is 14. And if the pH is 14, the pOH is 0. If the concentrations of H plus increase, the pH will be decreased. And if the concentrations of hydroxide ion increase, the pH will be increased. So to combine the relationships between the concentration of H plus, pH, OH minus, and pOH, let's say that if the concentrations of H plus increase, the pH will be decreased, and the concentrations OH will be decreased and the concentrations of pOH will be increased. And this one is the formula that we can use to calculate pH or pOH. That is pH plus pOH equal to 14.